Swayam Prabha. Digital India. Educated India.
Welcome to Module 55 of Point-Set-Topology Part-I. So today we shall study the separation axioms, freshness, Hausdorffness, regularity, etc., comparing one with the other. So that is why the word hierarchy here. Which one is stronger than which? So that is the main question here. Okay. For example, you have already seen that Hausdorffness implies freshness. On the other hand, we cannot compare directly regularity or normality. Okay. Similarly, we can't compare Hausdorffness and regularity. Okay. However, if you mix up these two, okay, then something quite surprising thing comes out. There is a complete hierarchy, you can take. So once there is such a hierarchy, we will have to use numbers to indicate them. I mean, classically they have been done like that, so we have to follow it. There is no other choice. Okay. I want to warn you that there are some authors who do the other way around, which is totally unexplainable. I don't know how they have got into that mess. Like very good book like Simon's book has a different connotation altogether. So my connotation is different from that. So you have to be careful about that. So I would prefer that the terminology I am following is more logical than the other part. So I just want to warn you, that's all. So we shall call a Frechet space a T1 space and a Hausdorff space a T2 space. Okay, a space which is T1 and regular will be called T3 space. And a space which is T1 and normal will be called T4 space. So this is what I meant by mixing up. T1 and regular will have a name, namely T3. And T1 and normal will have a name T4. T1 and completely normal will be called as T5. Now, why these numbers? These numbers have been chosen with some results already in mind. Namely, a Tn, where n is bigger than m, will always implies Tm. So T5 implies T4, implies T3, implies T2, implies T1. So that is the hierarchy. That looks like a beautiful way of putting it and easy to remember thing also. Okay, so that is the theorem, first theorem here. Okay, so I will come back to these two things a little later. So I will come back to that one. So first let me go through this theorem. I greater than or equal to j, we have Ti implies Tj. Okay. So Ty implies T4 is obvious. T5 being completely normal plus T1. T4 is normal plus T1. Okay. So completely normal implies already normal. So that is obvious. Though normality itself does not imply regularity, if you put T1 on both sides, there is an implication. Why? Because as soon as T1 is there, okay, singleton sets become closed. Therefore, if you have a singleton point and a closed set disjoint from that, it's as if you are having two disjoint closed subsets. Therefore, normality, you can assume that there are open subsets around that which are disjoint. So T1s assures that singleton points are closed. That's why this works. All right. Now T4 implies another one. I will come to that one later on. First, I will want to complete. So now T3 similarly implies T2. Why? Because T3 is a closed set and a single point. But single point is closed, and when you take two distinct points, they are both closed subsets. So you can apply regularity to get two open subsets around that one. So that implies Hausdorffness. So T1s helps to derive regularity from regularity Hausdorffness. Only under T1 they will be equivalent. That's what we have seen already. Otherwise, it's not true. And already we have seen T2 implies T1. Okay. Now I go back to this other numbers here. One number is, so I will go back to that one. So we are introducing a little more, few more numbers here. Let me come back here. A T1 space which is completely regular. Remember, there was a regularity and complete regularity also we have introduced. Okay. So T1 space which is completely regular will be called as T3.5 space. Unfortunately, there is no integer between 4 and 3. So you have to take 3.5. The whole idea here is that T4 implies T3.5, and T3.5 automatically implies T3, because complete regularity implies regularity. Add T1 on both sides, you get T3.5 implies T3. But what is true is that T4 implies T3.5 because of Urysohn's characterization. Remember that. T3 and this complete regularity was actually an adapted version of Urysohn's characterization, right? So that is the whole idea. So this T3.5 has another name. It's called Tikhonov space. Okay. So there was no integer to accommodate it. So people cooked up this T3.5 name for it. That's all. But there is another thing one can do. A weaker version of T1. Okay. So let us define that one. We have not done that one yet. So there is no regularity, normality, anything. It is weaker than T1 space. What is it? A topological space is called T0 space. So this time we are jumping, not T half and so on. T0 space. If for every pair xy of points in X, okay, when I pair, I mean X and Y distinct. There exists an open set U containing X and not containing Y, or an open set containing Y and not containing X. I repeat, given two distinct points, you may have an open set around the first one, not containing the second one, or it may happen that there is an open set containing the second one but not the first one. It just means that both of them can also occur. I'm just saying or. I'm not saying either or. Okay? I'm not saying only this or only that. No. The point is both of them can also occur. So that I don't have to tell that, but I want to make that one clear. Okay. In the definition above, we have used the word or, not either or. So it may happen that both are true, as in the case of T1ness. In the case of T1ness, if you have two distinct points, there is a neighborhood about one which doesn't contain the other. Now I don't say which one. Okay, therefore it is applicable to both the points there. Right? So that is why a T1ness automatically implies T0, but T0 may not imply T1. Okay, so this T0 space is just looks like a cooked up notion for, that is my opinion, cooked up notion from freshness. There is only one instance wherein some extra hypothesis there, wherein T0ness will imply T1ness. We will see that one. Okay, there is only one instance of that one. So anyway, the numbering is completely justified because of our theorem now. T5 implies T4, implies T3.5, implies T2, implies T1, implies T0. Okay, so this is complete hierarchy. All right. Whenever I is bigger than j, Ti will imply Tj. Okay, so here is another example now, which is a Hausdorff space, but not a regular space. Okay. See, Hausdorffness does not imply regularity. Regularity does not imply Hausdorffness either. But regularity plus T1 implies Hausdorffness. Okay? Hausdorff is same thing as T2. So here's an example which is Hausdorff but not regular. Again, on the real line, we take the collection tau of all subsets U which satisfy the following condition. Given x belonging to U, there exists an open interval I such that x is inside I, but instead of saying that I is contained inside U, which will be the usual topology, what we say, I intersection Q is contained inside U. A much weaker condition. Okay. If the whole of I is contained inside U, well and good. That will be usual topology. But this is much weaker condition. Okay. Nevertheless, this condition defines a topology on X, namely R. With this topology, R will be called rationally extended topology. Okay, that is the name. Obviously, it is finer than the usual topology because usual topology satisfies this condition, right? The whole of I will be contained inside it. Once it is finer than the usual topology, it is Hausdorff. Anything finer than a Hausdorff space is Hausdorff. So half the part is over. So what we want to prove is that it is not regular. Okay. For seeing that it's not regular, we take f equal to Q complement, set of all irrational numbers. The set of rational numbers is an open subset here, right? Because take a point in the rational numbers, take any interval, all the rational points in the interval are contained inside Q. That's all. So Q itself is open. Therefore, Q complement is a closed set. Okay. Now take x equal to 0 or any rational number for that matter. Let's take x equal to 0. That is outside, right? So we must find what? We must find u and v such that x belongs to u and f is contained inside v. U intersection v is non-empty. That is regularity. But now we have to show that no matter what u and v are, the moment they are open and contain x and f, their intersection is non-empty, is what I have to show. To conclude that the space is not Hausdorff. We could have chosen any other point, we could have chosen any other thing, but this is our choice. So f is QC. So we will try to do this one. If it fails, doesn't mean that it is regular, because we have made a choice here already. Okay. So assume that U is an open subset containing X and containing 0, and V is an open set containing all the irrational numbers. That is what we have started with. So since it is an open subset, U is open subset, there will be an open interval such that this X is inside I. Remember, X is just 0. You can, or any rational number. X belongs to I, and I intersection Q is contained inside U. Okay. So I is an open interval. Therefore, you can take any S inside I intersection F. What is F? F was set of all irrational numbers. So it has a lot of irrational numbers. Okay, obviously this S will be different from X, no problem. Then there must be another open interval J such that S is inside J, J intersection Q inside V, because V is an open subset containing F by our assumption. Okay, look at these two intervals I and J. Okay, they have a common point S. I and J are open intervals. There is a common point S, means they are intersecting. So intersection of two open intervals, if it is non-empty, must be another interval only, right? Therefore, since S is I intersection J is a non-empty open interval. But then this non-empty open interval intersection with Q is also non-empty. Now, if you look at J intersection Q, that is inside V. But if you intersect I intersection Q, that is inside U. Therefore, this intersection is both inside U and V, so U intersection V. That is the thing that we wanted to prove, that such open subsets cannot be disjoint. So that proves that the rational extended topology on R is Hausdorff, but not regular. Okay. Can it be normal? Can it be normal?
No.
Why?
Because we have seen that T3 implies T4.
The other way around. T4,
Yeah, T4 implies T3.
Normal plus T1 implies regular plus T1. So T4 implies T3. But we have seen that it is not regular. But it is Hausdorff, so it is T1. Okay. So it follows that this cannot be normal either. So that is a corollary once you prove that it is not regular. Okay. Now we will take another example, which will give you regularity does not imply normality. This space is regular, but not normal. Okay. We have already seen such an example, but we would like to do this one for reason that this again another modification of the real topology, Euclidean topology. So in exercise 4.48, we have indicated that the semi-interval topology product with itself is completely regular but not normal. See, what we have proved is regular and not normal, but it's actually completely regular is what we have indicated in the exercise. There it was an exercise, okay, but now we will prove this one, the other example. This is not regular, this is regular but not normal, okay. So what I do, I take the upper half plane H, all xy belonging to R2, y positive. Okay, the second coordinate is positive, the upper half plane, open upper half plane. I am denoting L by L, the real line R cross 0, y equal to 0. Okay, I am including that also in the along with the upper half plane, and that is my X. So this is the closed upper half plane, but I don't want to call it that way because this part I can call it as upper half plane, but here I'm going to change the topology, so I am using a different notation X here. So here is the topology coming now. Two subbases are declared. S1 is equal to set of all open balls, okay, around points inside capital H, namely y coordinate is positive, x coordinate anything, b epsilon of xy. It must be contained inside H, therefore the radius must be less than y, that's all. 0 less than epsilon less than y. So I am taking all the open balls completely contained inside the upper half plane. Okay, these are standard open balls, right? The second one is slightly different. That is where the crux of the matter lies. They are open balls x comma y center. The radius is equal to y, not epsilon. So y coordinate becomes the radius of that. Okay, so it is touching the x-axis, right? And one point, what is that point? X comma 0. So you include that also. That point is not there here, but it's tangential. So include that point also. That is one of the elements in this set, such that xy's are inside H. Okay, start with a point in the upper half plane, take the maximum open ball contained inside that. That is the meaning of this byxy. Okay, you can't take bigger than that, then it will go below the x-axis. That is not allowed, right? So if you take maximum open ball, this is what it is. Then put that point x comma 0 also in that. So this is going to be one of the sets inside this S2. So take collection of all of them. So that is your S2. Now you put the union of these two, call that as S, a subbase for a topology on X. Any collection of subsets can be declared as subbase, that we know. Okay. So this is subbase for topology on X. Whatever that topology is, it has the property that, by the way, I have made a remark here, namely, this is actually a base. Let us not bother about this. This is subbase is enough for us. Note that this topology is finer than the Euclidean topology. because you see on the upper half part, this is actually Euclidean topology. Okay, everything open in the R2 is there and vice versa. On the x-axis, you intersect these balls with the x-axis. What is it? It is just the single point, x, 0. Therefore, each singleton point on the x-axis becomes an open set. Therefore, the induced topology on the x-axis is discrete. In any case, it's finer than the usual topology. All right. Therefore, this entire topology is finer than the usual topology. Okay. In particular, it is Hausdorff. So Hausdorff's theory. All right. And now we have to show that this is not what? This is not normal. So I want you to observe this, namely, if you take by xy union the singleton x0, okay, that is an open subset of this topology. It is in a second part of S2 part. Its closure is all those A, B belong to R, such that x squared minus a squared, actually, yeah, a square plus y square minus b square is less than or equal to y. The full, the full ball will come when AB reigns over all R. Okay. So the closure will be just the closed ball, that's all. That's what xy is already there, but the closure will contain all the rest of the circle also. That's all. Regularity at points of edge follows easily by the Euclideanness of the upper half plane. Take a point in the upper half plane, take an open subset. You don't have to worry about weird open subset, but you can take inside that, you can take a regular open set, open ball, right? And verify the regularity. It's already Euclidean space, so it's regular. So there is no problem. The problem arises when you take x cross 0 inside L, namely on the x-axis. Okay. For x comma 0 belonging to L and U is an open set containing it. Okay. There exists a y positive such that by xy inside U. So these are because these are basic open sets. Now we can take V equal to by xy1 union x0, where the y coordinate, the y coordinate is less than 1. Okay. And then check that V bar less than y, sorry. And then check that V bar is contained inside U. Okay. So even for points on that one, you can verify that it is regular. To see that x is not normal is our point here. Okay. So for not normal, we again take A equal to the entire Q and B equal to R minus Q. Okay, similar to the earlier example. Okay, then we will show that there is no open subsets containing A and B which are disjoint. Okay, so that is what we want to show. It's similar to R cross L, but somewhat easier, maybe you can say. For each R in R, choose YR positive such that BYR, R comma YR, YR positive, R comma YR will be in the upper half plane, right? Now I am taking a full ball, maximum ball of whatever possible radius, that will be radius will be yr. Put the r also, this is an open subset now. So such an open subset will be inside G, where G is either U or V accordingly, wherever you are, R may be inside U or inside V. That means rational or irrational. Okay, for both of them, argument is same. Okay, so you can change, you can use such a thing. That is always such a thing, so that this is contained either inside U or inside V. According, R is inside A or B. Now for n inside n, let us define Fn to be all S inside B, okay, such that Ys coordinate, okay, is bigger than 1 by n. See, for each R, I have a yr, okay, I have chosen. So I look at all those S such that its Ys is bigger than 1 by n. So that is my definition of Fn. Then for everything, some yr is positive is what it has said. So entire of B will be union of Fn's. After all, once it's positive, it will be bigger than some 1 by n. So B is union of Fn's. Now, by Bayer's category theorem on R, okay, with the usual topology, see, remember what is B? B is set of all irrational numbers. It follows that interior of Fn bars cannot be empty for all of them. Right? We have shown that the entire, we have actually shown that even irrational numbers cannot be written as countable union of no-reductant sets. Because then you can add another set of countable numbers containing R, the whole of R will be written like that. So that is why one of the Fn's must have property that interior of Fn bar is non-empty for 1n. You fix such an integer now. Okay, so by looking at these definitions of this one, and so far we have not used anything other than that A and B, U and B are open. Okay, nothing else other than. But now one of these has interior of Fn bar is non-empty. Okay, choose an open interval I contained inside Fn bar. Interior in the usual topology, these are all subsets of R now. So there will be an open interval containing this one. And a rational number now R belongs to I. If epsilon is chosen appropriately, we claim that for any irrational number inside, see this S belongs to R minus epsilon, R plus epsilon. R is contained inside this interval. Now, for every epsilon, for every S inside this R minus epsilon, R plus epsilon, which is obviously I have chosen so that it's contained inside I, and which is contained in Fn bar. But I am not saying that for all epsilon is true. Appropriately chosen epsilon, what we will have is BYR, RYR, intersection corresponding S is BYS, SYS will be non-empty. That is a contradiction, because these things are supposed to be contained inside two disjoint open sets. Okay, this once is R is rational number and S is irrational number. Okay, so that will imply that U and V are, U intersection V is non-empty. Okay, so this is our claim. How to choose epsilon is the point, so that this will happen. So here is a picture of what is happening here. Whatever R and S, whatever they are, there is some YR. Okay, so this whole open ball along with this point is inside U or inside V. That's how we have got it. Now I want that S and R are chosen such that they are intersecting here. Okay, all that I am chosen, R has been already chosen. S should be chosen close to R in such a way such that the corresponding ball will intersect this one, because SYs are already chosen. I have no control over that. But I can choose S itself closer and closer to R. So how close I should choose is indicated in this picture. Okay. So now I have just worked out 12 standard mathematics here. So 31 is true. That means the intersection is non-empty if and only if R minus S squared plus YR minus YS squared. This is the distance from whatever you see, the Euclidean distance is less than YR plus YS squared. So that is what I am playing, R minus S squared. So go back to this picture. R minus S squared, this distance, okay, minus YR or RY. I have written RY, YR should be. The YR minus YS, Y coordinate distance squared. So that is the distance between these two. This distance, total distance, must be less than the length of this one plus the radius of this plus radius of that. It's YR plus YR. So there is notation difference here. YR, this is YR and YS. That's all. Okay. So that is the first condition. YR plus YS, they are a radius, sum total. If I take the square root of this will be square root of that. So I have taken the square of this one, this must be less. Okay. This is same thing as now simplify. R minus S squared is less than 4 times YR into YS. You take this one to on this side, YR square, YS square will cancel out. Okay. Twice YRS will add up. It will be 4 times YR, YS. The same thing as now taking square root. Modulus of R minus S should be less than twice square root of YR, YS. Okay. Therefore, choose now epsilon to be less than twice the square root of YR by N. Okay. Suppose you choose this YR by N. It follows that. Now, what is this N? Remember, this N was fixed so that the interval is contained inside the interior of Fn closure. So that N appears here. It follows that R minus S is less than epsilon. If you have this one, this epsilon is less than twice YR by N. That will be less than twice YR YS square root. I want this one. I want the last thing. If I have satisfied this R minus S less than this one, then the intersections will be non-empty. The 31 will be true. So now I choose this epsilon to be less than this one, and R minus S less than epsilon will satisfy this property. Okay. So this is because YS is bigger than 1 by N. So that YS part disappears here. You see, some condition should not be depending on S, so that I am choosing S. So this is purely in terms of R now. Okay, so that will be automatically less than this one, because YS part is less than 1 by N. So this completes the proof that X tau is not normal. So here is some exercises. Maybe you can have your own exercise also, but I would not like to encourage you to go on studying just counterexamples. Nevertheless, if you are interested in, there is a very good book written on this one long back. Okay, I have given the reference right in the beginning, so I will indicate it to you later, so you can read that book. Okay. So thank you. We will meet next time now. Okay.